We end tonight with the clearest pictures yet of Neptune, the most distant planet in our solar system. We're looking at Neptune's orbit, and it's not following Newton's laws. When Neil deGrasse Tyson made his unexpected revelation about Neptune, it didn't just ripple through the community of astronomers, it shook the foundations of what many thought was a well-understood corner of our solar system. Tyson, known for his articulate communication of complex astrophysical phenomena, addressed a packed auditorium during a recent symposium that was being streamed worldwide. The world watched in astonishment as he unveiled findings suggesting that Neptune, the ice giant lurking at the fringes of our planetary family, may not be what we have long assumed it to be. Before we start, smash the like and subscribe buttons for more updates. For decades, Neptune had been quietly classified as the eighth planet from the Sun, a cold bluish orb of gas and ice orbiting far beyond the familiar warmth of the inner planets. It was discovered in 1846 not by direct observation but by mathematics. Its position was predicted due to irregularities in Uranus's orbit. Since then, Neptune had been understood through a steady trickle of telescope data and a singular flyby by Voyager 2 in 1989. That fleeting visit gave us precious snapshots and surface-level data that framed the planet as a frigid dynamic world with supersonic winds, massive storms, and a distinctive deep blue hue. But even with all that, much of Neptune remained shrouded in mystery. Tyson's disclosure cracked that veil wide open. The central point of Tyson's announcement centered on a series of recent observations made using a combination of data from the James Webb Space Telescope and Earth-based interferometric arrays, which revealed anomalies in Neptune's internal composition and behavior that do not align with our current models of gas and ice giants. According to Tyson, what astronomers detected defied the conventional understanding of Neptune's internal layering and magnetic field generation. These instruments uncovered patterns in Neptune's gravitational field, electromagnetic emissions, and even thermal output that hinted at an interior far more complex and volatile than anyone had anticipated. What Tyson described was a Neptune with layers not simply arranged by density or temperature but disrupted by dynamic churning movements that seemed to violate standard thermodynamic expectations for a planet at such a distance from the Sun. Instead of a smoothly differentiated interior with a rocky core, a layer of icy water and ammonia, and a gaseous outer envelope, Neptune appears to be host to a mosaic of interacting zones with intermittent regions of plasma-like materials and inexplicably warm patches buried beneath the cloud tops. These warmer regions shouldn't exist under traditional models. Solar energy is far too weak at Neptune's distance to account for them, and there is no evident tidal heating from nearby moons of significant mass. Something internal is generating more heat than expected. Even more perplexing was Tyson's disclosure about Neptune's magnetic field. The planet's magnetic field is already known to be unusually tilted and offset from its center. But what recent data show is that the field is not just skewed but behaving erratically over time. Its structure seems to be in flux, with sections of the field appearing to drift and reform in cyclical patterns not previously observed. This has led to the hypothesis that Neptune's internal dynamo, the mechanism by which it generates its magnetic field, may not resemble those of other planets at all. Instead of a convecting metallic core or a layer of conducting hydrogen, Neptune may have a shell of exotic ices undergoing chemical transformations under immense pressure, producing charged flows that drive this shifting magnetic map. Tyson elaborated on a possibility that sent a murmur through the scientific community that these strange features might indicate that Neptune is partially hollowed or at least composed of stratified cavities or pockets that act like resonant chambers for electromagnetic and gravitational energy. This idea, still speculative but increasingly discussed, could revolutionize planetary science. A planet with such internal architecture would behave in fundamentally different ways from the solid or gradually compressed spheres that most models assume. The implications of Tyson's revelation are profound. If Neptune deviates so radically from our current planetary models, it opens the door to re-evaluating the formation history of our entire solar system. Neptune, after all, is thought to have migrated from a different region of the solar system after forming. Its gravitational interactions have shaped the Kuiper belt, disturbed other planets' orbits, and possibly even influenced the ejection of what some theories suggest was a fifth giant planet in the early solar system. If Neptune itself is a more chaotic or exotic entity than previously believed, the story of our solar system's adolescence might be far messier and more dynamic than textbooks have described. Another startling point raised by Tyson was the detection of irregular radio emissions emanating from Neptune's atmosphere. While the planet is known to emit radio waves due to interactions between its magnetic field and solar wind, the new emissions appear to originate from deeper within the planet, and their frequencies are not consistent with what's been observed from natural atmospheric activity alone. Some researchers are now exploring whether these emissions point to internal processes unlike anything previously recorded in the solar system, potentially hinting at quantum-level behaviors occurring in Neptune's dense interior or even unrecognized natural phenomena born from the strange chemistry under crushing pressures. Adding to the intrigue is the suggestion that Neptune's atmosphere may be hiding layers of exotic materials not previously confirmed to exist outside of laboratory simulations. Tyson highlighted growing evidence that the planet may host superionic ices, materials that behave both like solids and liquids, where water molecules lose their hydrogen atoms, creating a kind of slushy electrified soup. This phase of matter could not only explain some of Neptune's heat generation and electromagnetic peculiarities but might also be a major component of its overall structure. These ices, under extreme pressures, might move in vast conveyor belts beneath the surface, creating currents and turbulence far more complex than those seen on Earth or Jupiter. Further, Tyson discussed the planet's extreme winds, which reach speeds exceeding 1,300 miles per hour, in a new light. Traditional models have attributed these winds to differential heating and rotation dynamics, but recent studies suggest that internal thermal pulses could be driving these winds from the inside out rather than from atmospheric interactions alone. If Neptune is self-stimulating its weather systems via deep thermal instabilities or even phase transitions between materials under pressure, it would mark the first known example of a planet whose weather is primarily driven by internal dynamics rather than external solar energy. The revelation even has implications for exoplanet research. Neptune-sized exoplanets, often labeled mini-Neptunes or sub-Neptunes, are among the most commonly detected types of planets outside our solar system. If Neptune is fundamentally different from what we assumed, then so too may be those thousands of similarly sized worlds now catalogued by missions like Kepler and TESS. The classification and modeling of those planets may need to be revisited, and Tyson's presentation emphasized how our assumptions about composition, habitability, and evolution could be dangerously off base. Tyson also highlighted one tantalizing though highly theoretical consideration that Neptune's anomalies could make it a candidate for previously dismissed models of failed stars or transitional celestial bodies. While Neptune does not come close to the mass required for fusion, its unusual internal heat and dynamic energy systems may place it in a gray area that demands new categorization. It may represent a class of objects that are not quite planets and not quite brown dwarfs, challenging the binary labels that have dominated astronomical classification for centuries. This redefinition of Neptune could have consequences not just for how we label and understand planets but for how we imagine planetary evolution in a cosmic context. It suggests a greater diversity of planetary types than previously considered, not just in size and atmosphere but in fundamental architecture. Tyson's description of Neptune as possibly being a chaotic system in equilibrium was both poetic and revolutionary, a body that contains self-balancing forces in constant flux, driven not by the quiet decay of energy but by the eruption of it from unknown processes deep within. These insights also underscore the critical role of advanced observational tools. Without the James Webb Space Telescope and recent ground-based array upgrades, these signals and patterns would have remained hidden beneath the planet's shrouded surface. Tyson's emphasis on this point was clear. Our capacity to truly understand the universe is intrinsically tied to the instruments we build to observe it. As our lens into the cosmos sharpens, so too does the possibility that we will uncover more worlds like Neptune, complex, misunderstood, and waiting to rewrite everything we think we know. The ripple effects of such a revelation will inevitably stir discussion around the limits of current scientific modeling. If one of our own planets can surprise us this dramatically, then what lies beyond Neptune, previously seen as the colder, quieter cousin of the inner gas giants, has been thrust into the spotlight as possibly the most exotic member of the solar system. And with it comes a reminder of just how little we truly understand the universe we inhabit. Tyson's announcement is not just about Neptune. It is about our hunger for knowledge, the humility of science, and the thrilling unpredictability of discovery. If you like this video, please give it a like and subscribe to our channel. Also leave your comments below and tell us what are your thoughts on Neptune. Expect surprises. Will Tyson change what we believe? We want to hear from you. Thank you for watching and see you next time.